Okay, the previous video covers the important theoretical points in sections 4 and 5 on bases and dimension. This video is going to talk about some examples and the homework problems. So let's look at example 6. It says find the basis for the subspace spanned by these 5 vectors. So these are vectors with 4 components, so this subspace is a subspace of R4. But what's the dimension and what would be a basis? Well, dimension can't be more than 4 because it's a subspace of R4. So these 5 vectors can't all be independent, but maybe a basis for it might be 4-dimensional or it might be less than 4-dimensional. You really can't tell. So how do you tell what the dimension of the space spanned by these 5 vectors is, and how would you find a basis? Well, what you do is put those 5 vectors in as the rows of a matrix, and we're trying to find a basis for the row space, the space spanned by the rows. And what you do is reduce it down to reduced row echelon form, because that doesn't change the space spanned by the rows. That is, you switch 2 rows, that obviously doesn't change the space spanned by the rows. You multiply a row through by a non-zero scalar, that obviously doesn't change the row space either, the space spanned by the rows. And if you add a multiple of one row to another, whatever you can form with linear combinations, the original rows is the same as what you can form with linear combinations of the final one. So the final row echelon form, these rows span exactly the same space, the original space spanned by these 5 columns. But the 2 rows of zeros, you can throw those out because you don't need those to span the space. Any multiple of 0 is 0, so they do no good whatever. So the row space, the space spanned by these 5 vectors is spanned by these 3 vectors, the non-zero vectors. So you throw out the 0 rows, and the remaining, the non-zero rows form a basis for the row space because they are clearly independent. The first vector can't be a linear combination of the second and third because second and third have zeros and it doesn't. Similarly, the second row can't be a linear combination of the first and third because they both have zeros, so any linear combination will have a 0 in the second component and so forth. So we reduce it down to row echelon form. The space spanned by the final matrix, rows of the final matrix, is exactly the same as the space spanned by the original rows. And now it's obvious that the non-zero rows form a basis and the 0 rows can be thrown out. So in the homework in section 3.4, problems 11 through 15 say find a basis for the row space, which means you just reduce down to reduced row echelon form, throw out the rows of zeros, and the ones left are a basis, and the number of non-zero rows, the number of vectors in a basis, is the dimension of the row space. The first few here are basically find the null space of a matrix. It says find all vectors with 4 components, that is subspace of R4, such that these 2 equations are satisfied. This is just the null space of the matrix 1, 1, minus 1, 0, 0, 1, 0, minus 1. So you solve that AX equals 0 in the usual way and write the solution in vector form, and you'll end up with 2 arbitrary variables, and you write it in vector form, and you'll see what the basis is. The general solution is something times this vector plus something times that. Therefore, these 2 vectors form a basis. Therefore, the dimension of the null space is 2. These problems say find a basis for the span of S. So you want to know a basis for the space spanned by these 4 vectors. Say these are 4 vectors in R3 because they have 3 components. You just put those 4 vectors in as the rows of a 4 by 3 matrix, reduce it down to row echelon form. You're guaranteed to have at least 1 row of zeros. You might have 2 or more. throw out the 0 rows. The ones remaining form a basis for the row space. Now remember, there are a lot of spanning sets and a lot of bases, so that makes it hard to grade these problems because there are so many different possible bases. But the obvious one is to put the rows in as put the vectors in as the rows of a matrix, reduce it down to echelon form, throw out the rows of 0, and the non-zero rows form a basis. The last problems here say determine whether these set of vectors form a basis for all of R3. Well, we know that the R3 has dimension 3, so any basis for R3 has to have 3 vectors, but any 3 vectors are not necessarily a basis. They have to be independent, so you put these in as the rows, reduce it down, and if you don't have any rows of zeros in that 3 by 3 matrix when you finish, then they do form a basis. This one, these can't possibly form a basis for R3 because there's too many vectors. They can't be independent. 4 vectors in a 3-dimensional space have to be dependent. One has to be a linear combination of the others. So this one has too many vectors to be a basis for R3. If you put those rows in as put those vectors in as the rows of a matrix, reduce it down, you're guaranteed to have at least one row of zeros, so they're not independent. This one only has 2 vectors, so it can't possibly be a basis for R3. This one has 3 vectors, so it's got the right number, but it may or may not be a basis depending on whether they're independent. So you have to reduce the matrix down whose rows are these 3 vectors and see if you end up with a row of zeros or not.